On April 27, 2023, astronomers around the world scrambled to point their telescopes at the same patch of sky. The alert had come from a gamma-ray space telescope, a satellite whose entire job is to sit above Earth's atmosphere and wait for the universe to do something violent. And something had just happened that the field had never seen at that scale before. A burst of gamma rays, the most energetic form of light in existence, had struck Earth's atmosphere with a brightness so extreme that it briefly overwhelmed the detectors designed to measure it. Instruments that had been measuring gamma rays for decades. Instruments that had cataloged tens of thousands of previous bursts simply saturated. The photon flux was too high for the sensors to count individually. The event was so bright it temporarily distorted measurements of Earth's ionosphere from the ground. Its afterglow was visible in optical telescopes for days. The source was a galaxy 2.4 billion light-years away. The energy released in approximately 10 seconds was comparable to the total energy the sun will radiate over its entire 10 billion-year lifespan. In 10 seconds, from a source the size of a city, more energy was released than the sun will produce in the age of the universe. Astronomers named it the Boat, the brightest of all time. GRB2210009A. The most energetic gamma ray burst ever observed in recorded history, surpassing anything in a dataset stretching back 55 years. And this one was 2.4 billion light-years away, one of the closest ever detected. Gamma-ray bursts are not a hypothetical threat. They are not a theoretical catastrophe category. They are real events happening in real galaxies at a rate of roughly 1 to 2 per day across the observable universe. Every day, somewhere in the cosmos, something releases more energy in seconds than the sun will produce in its lifetime. We know this because we can see it happening. We have seen it happen over 10,000 times. We have caught them in the act, tracked their afterglows, identified their host galaxies, measured their energies, classified their types. And we have worked out, with increasing specificity, what would happen to Earth if one of the right kind went off at the right distance in the right direction. The answer is not reassuring. This video is about gamma-ray bursts. What they are, what creates them, how they work, why they are the most energetic events in the universe since the Big Bang itself, and what they would do to a planet like ours. We will start with the discovery, because the discovery is itself extraordinary. We will move through the physics, because the physics is what makes the terror specific rather than vague. And we will end where the science ends, at the honest, carefully bounded answer to the question of whether a gamma-ray burst represents a meaningful existential threat, not just to life as it exists on Earth today, but to life anywhere in the universe that happens to be in the wrong place at the wrong time. Chapter 1. The Discovery Nobody was looking for. The story of gamma-ray bursts begins not in an observatory, not in a university department, but in a classified military satellite program at the height of the Cold War. In 1963, the United States and the Soviet Union signed the Partial Nuclear Test Ban Treaty, which prohibited nuclear weapons testing in the atmosphere, in space, and underwater. The treaty was a diplomatic achievement, but the U.S. military had an immediate practical problem. How do you verify that the Soviets are actually complying? Nuclear explosions in space produce a distinctive pattern of gamma rays, the same high-energy photons produced by nuclear fission and fusion reactions. If you could build satellites sensitive enough to detect gamma rays, you could catch clandestine nuclear tests in space. The satellites built for this purpose were called the Vela satellites, from the Spanish word for watchman. The US launched pairs of them in a series of missions beginning in 1963, placing them in high orbits where they could monitor the Earth and near-Earth space for the gamma-ray signature of a nuclear detonation. They were extraordinarily sensitive instruments designed by military engineers at the Los Alamos National Laboratory. They found no Soviet nuclear tests in space. What they found instead, on July 2, 1967, was completely unexpected. A burst of gamma rays coming not from anywhere near Earth, but from deep space. The signal had none of the characteristics of a nuclear explosion. It rose rapidly, peaked, and decayed in a way that was inconsistent with any known terrestrial or near-Earth source. The satellite team, Ray Klebsadel, Ian Strong, and Roy Olson at Los Alamos, confirmed the detection, checked it against multiple satellite records to determine that it was not an instrument anomaly, and then sat on the result for 6 years. The data were classified. The military was not eager to announce that its nuclear detection satellites had found something strange coming from the cosmos. The finding was finally declassified and published in 1973 in a paper in the Astrophysical Journal Letters titled Observations of Gamma Ray Bursts of Cosmic Origin. The paper reported 16 gamma ray burst events detected by the Vela satellites between July 1969 and July 1972. The authors were careful not to speculate about the origin. They simply reported what they had seen. Brief flashes of gamma rays coming from cosmological directions with rise times of a fraction of a second and durations ranging from less than a second to about 30 seconds. They had no explanation. There is an irony embedded in this history that is worth noting. The Vela satellites were built for military threat detection, classified under Cold War secrecy, and deployed at enormous expense to find nuclear tests that never materialized in space. What they actually found? One of the most important astrophysical discoveries of the 20th century, sat in classified military files for 6 years before being shared with the scientific community. The delay was not due to any conspiracy or malice. It was simply the standard handling of classified data from a classified program. Klebsadel, Strong, and Olson could not publish until the program was declassified. When they finally did, the discovery landed in a field that had no framework for understanding it, and it took another 24 years to establish even the basic fact that the bursts were at cosmological distances. The scientific bureaucracy of national security delayed by 6 years a discovery that then required another 24 years to explain. Had the data been public from 1967, the field might have had different tools and a broader scientific community working on the problem sooner. The history of GRB science is also, in a minor way, a history of the costs of secrecy in science. The publication triggered immediate interest in the ORI astrophysics community, followed by 2 decades of sustained confusion. The problem was fundamental. In the 1970s and 1980s, astronomers could detect gamma ray bursts and measure their arrival times and energy spectra, but they could not determine their distances. Without knowing how far away the sources were, they could not calculate their intrinsic luminosities. A burst could be a weak, nearby event, or an extraordinarily powerful, distant one. The entire question of what kind of physical phenomenon was responsible was hostage to this distance uncertainty. The first clue about distances came from the BATSI instrument on NASA's Compton Gamma Ray Observatory. Launched in 1991, BATSI detected gamma ray bursts at a rate of approximately 1 per day and accumulated a large enough sample to perform meaningful statistical analysis. The result was striking. The bursts were distributed isotropically across the sky. They came equally from all directions, with no concentration toward the galactic plane and no concentration toward the galactic center. This isotropy strongly suggested that the sources were either very close to Earth, within our solar neighborhood, before the large-scale structure of the galaxy becomes apparent, or at cosmological distances, so far away that the structure of the Milky Way is an irrelevant local detail in a universe where sources are distributed uniformly in all directions. The nearby hypothesis was rapidly ruled out on statistical grounds. There were not enough potential source types within the solar neighborhood to account for the observed rate. The cosmological hypothesis became strongly favored. Gamma ray bursts were happening in distant galaxies. But this implied energies so enormous, if the burst was radiating equally in all directions at the observed flux from billions of light years, that many astrophysicists found them implausible. The implied energies were in the range of 10 to the power of 51 to 10 to the power of 53 joules or more. Something in the universe was releasing, in seconds, the energy equivalent of converting a solar mass of matter entirely into energy. The debate was settled definitively in 1997 when the Italian-Dutch Beppo-Sachs satellite, designed specifically to provide rapid, precise positions for gamma-ray bursts so that ground-based telescopes could follow up, detected a burst, localized it to within a few arc minutes, and enabled optical astronomers to find the fading afterglow. The afterglow's spectrum showed a redshift of 0.835, placing the source 6 billion light-years away. Not in our galaxy, not even in our neighborhood. Cosmological? The distance debate was over. Gamma-ray bursts were the most luminous events in the universe since the Big Bang. Chapter 2. 2 kinds of catastrophe. Not all gamma-ray bursts are the same. Within a few years of the initial BATSI statistical analysis, researchers noticed that the burst duration distribution was bimodal. There appeared to be 2 distinct populations with a dividing line at approximately 2 seconds. Bursts lasting less than 2 seconds were called short gamma-ray bursts. Bursts lasting more than 2 seconds, which constitute about 70% of the observed population, were called long gamma-ray bursts. This naming convention is blunt but has proven durable because the 2 populations turn out to have fundamentally different physical origins. Long gamma-ray bursts are produced by a specific type of stellar death, the collapse of a massive, rapidly rotating star, sometimes called a collapsar or failed supernova. Here is the sequence of events. A massive star, at least 20 to 30 times the mass of the Sun, and in many cases much more, reaches the end of its nuclear fuel. The iron core builds up through the successive burning stages we discussed in the previous script. Hydrogen to helium, helium to carbon, carbon to neon, neon to oxygen, oxygen to silicon, silicon to iron. When the iron core exceeds the Chandrasekhar limit, electron degeneracy pressure fails, and the core collapses in less than a second to nuclear density. In an ordinary core collapse supernova, the bounce produces a shock wave that blows off the outer layers of the star. But for the most massive, most rapidly rotating stars, something different happens. If the core is massive enough, above approximately 3 solar masses, the proto-neutron star formed at the center cannot sustain itself and collapses further, directly to a black hole. The outer layers of the star, which would otherwise be blown off in a supernova, begin to fall inward. But if the star was rotating rapidly, those outer layers have angular momentum. They cannot fall directly into the black hole. Instead, they form an accretion disk around it, a rotating torus of infalling matter that circles the newborn black hole at relativistic speeds, heated by viscous friction and magnetic processes, to temperatures of tens of billions of Kelvin. The accretion disk feeds energy into the system at an extraordinary rate. Through a combination of mechanisms, neutrino-antineutrino annihilation above the disk, magnetically driven Blandford-Zanayak extraction of the black hole's rotational energy, and pressure from the intense radiation. Twin jets of plasma are launched from the poles of the system along the black hole's rotation axis. These jets are narrow, typically a few degrees of opening angle, and they move at velocities very close to the speed of light. Lorentz factors of 100 to 1000, meaning the jet material is moving at 99.9 to 99.9999% of the speed of light. The relativistic jets punch through the outer layers of the collapsing star, which are still raining inward, and break out from the star's surface. Once the jets break free of the stellar envelope, they interact with the circumstellar medium and with themselves. Internal shocks, collisions between faster-moving and slower-moving shells of jet material, convert kinetic energy to gamma rays. The result is the prompt emission, the initial burst of gamma rays that lasts for tens of seconds to minutes and is what triggers the detection by gamma ray satellites. After the prompt emission ends, the decelerating jet interacts with the surrounding interstellar medium to produce the afterglow, fading emission at X-ray, optical, and radio wavelengths that can persist for days to years. The association between long gamma ray bursts and the deaths of massive stars was confirmed through multiple lines of evidence. Long GRBs are found in star-forming galaxies, specifically in regions of active star formation, where massive stars are most abundant. Some long GRBs have been directly associated with supernovae detected in the optical days after the burst, and the host galaxy properties match the environments where massive star formation is expected to be most active. Short gamma-ray bursts have a completely different origin. They come from the merger of two compact objects, typically two neutron stars, or a neutron star and a black hole, in a binary system. The merger happens after the binary has radiated angular momentum away through gravitational wave emission over millions to billions of years, causing the two objects to spiral inward until they collide. The merger produces an accretion disk around the remnant, which is either a black hole or a supermassive neutron star briefly before collapse. And the same jet launching mechanism operates, but for a much shorter time, because the accretion disk is less massive and drains more quickly. The connection between short gamma-ray bursts and neutron star mergers was confirmed spectacularly by the multi-messenger astronomy event of August 17, 2017, GW 170817, the gravitational wave detection accompanied by a short gamma-ray burst, and a kilonova that we mentioned in a previous script. For the first time, a gravitational wave signal from a merging binary and the electromagnetic emission from the resulting short GRB were detected simultaneously, confirming the long-suspected connection beyond any reasonable doubt. The distinction between long and short GRBs matters enormously for the question of where in the universe these events happen, and therefore for assessing their threat to inhabited planets. Long GRBs happen in star-forming galaxies, in regions of active massive star formation. Short GRBs, because the binary systems producing them require time for the compact objects to form and for the orbit to decay by gravitational radiation, can happen in older quiescent galaxies, far from active star formation. The distribution of GRBs across galaxy types provides important context for evaluating which of the two types is more dangerous to a planet like Earth, and in what kinds of galactic environments life might be at greatest risk. Chapter 3: The Energy Budget. Understanding the scale. Before examining what gamma-ray bursts would do to Earth, it is worth spending time understanding the energy scales involved, because the numbers are so far outside ordinary human experience that they require active processing to appreciate. The Sun at any given moment radiates approximately 3.8 times 10 to the 26th power watts. This is a staggering amount of power, roughly 26 million times the total electricity generation capacity of every power plant on Earth combined. Over the Sun's total 10 billion year main sequence lifetime, it will radiate approximately 1.2 times 10 to the 44th power joules of energy. This is the total energy output of the Sun for its entire existence. A typical long gamma-ray burst releases approximately 10 to the power of 44 to 10 to the power of 46 joules of energy in gamma rays alone, in a duration of seconds to minutes. The most energetic bursts, including GRB 221009A, the boat, release up to 10 to the power of 47 joules. That is the Sun's entire lifetime output, occurring in seconds. GRB 221009A alone released energy comparable to the entire electromagnetic output of the Sun over roughly 10 billion years in an event that lasted about 10 seconds. But wait, those energy figures assume isotropic emission, radiation spreading equally in all directions. A source radiating 10 to the power of 45 joules isotropically would be producing that energy in a sphere expanding in all directions. Real gamma-ray bursts are not isotropic emitters. They are tightly beamed. The gamma-ray emission is concentrated into a jet with a half-opening angle of perhaps 3 to 10 degrees. This beaming means that the isotropic equivalent energy, the energy calculated under the assumption of isotropic emission, significantly overstates the total energy budget. Correcting for beaming, the true energy release in gamma rays from a typical long GRB is approximately 10 to the power of 43 to 10 to the power of 44 joules. Even this corrected figure, 10 to the power of 43 to 10 to the power of 44 joules, is extraordinary. For comparison, the total energy released in a standard core collapse supernova is approximately 10 to the power of 46 joules, but 99% of that energy is carried away by neutrinos that interact negligibly with ordinary matter. Only about 10 to the 44th power joules ends up in the kinetic energy of the ejected stellar material, and only about 10 to the power of 42 joules, 1% of the kinetic energy, ends up as visible light in the optical supernova. A gamma-ray burst releases more energy in gamma rays alone than a supernova releases in optical light, despite the much smaller total energy budget, because the conversion efficiency of the GRB jet is extraordinarily high. The key number for the question of what a GRB would do to Earth is not the total energy release, but the energy fluence at Earth's distance, the energy per unit area received at Earth's location. For a source at a given distance producing a burst of gamma rays at a known flux, the fluence depends on the inverse square of the distance and the total energy in the direction of the beam. The relevant calculation for threat assessment is: at what distance would a gamma ray burst deliver a fluence sufficient to cause significant atmospheric damage to Earth? The answer depends on the specific mechanism of atmospheric damage, which we will examine in detail in the next chapter. But the preliminary answer from the first principles calculation is within roughly a few thousand to a few tens of thousands of light years, depending on the burst energy and the beaming geometry. A GRB within our galaxy pointed at Earth would be a catastrophic event. A GRB outside our galaxy, which is where essentially all detected bursts originate, is too distant to pose an immediate physical threat. The question then becomes, how likely is a gamma ray burst to occur within the dangerous range in our galaxy? And that question depends on the rate of GRBs in the Milky Way and on the specific environments in our galaxy where they are most likely to occur. Chapter 4. What it would actually do. The atmospheric mechanism. The specific mechanism by which a gamma ray burst would harm Earth is not what most people imagine. It is not primarily about the heat or the direct radiation or the electromagnetic pulse, although those are all relevant at close enough distances. The primary mechanism at distances of a few thousand light years is more subtle, more insidious, and in some ways more frightening: the destruction of the ozone layer. Earth's ozone layer is a thin band of ozone molecules, O3, concentrated in the stratosphere at altitudes of roughly 15 to 35 kilometers above the surface. It absorbs the most biologically damaging ultraviolet radiation from the sun, specifically UVB 280 to 315 nanometers, and UVC 100 to 280 nanometers, before it can reach the surface. Without the ozone layer, the UV flux at Earth's surface would be sufficient to cause rapid and severe damage to DNA in any organism exposed to sunlight, making most surface and shallow water ecosystems uninhabitable. A gamma ray burst striking Earth's atmosphere from space would deposit its energy primarily in the upper atmosphere, because gamma rays are efficiently absorbed by air. The energy deposition would ionize the nitrogen and oxygen molecules in the stratosphere, initiating a cascade of chemical reactions that produce nitric oxide, NO, and nitrogen dioxide, NO2. These nitrogen oxide compounds are extremely efficient catalysts for ozone destruction. A single NO molecule can destroy many ozone molecules before being removed from the chemical cycle. This is the same mechanism, nitrogen oxide catalysis, by which nuclear weapons tests in the atmosphere were once feared to damage the ozone layer, and by which chlorofluorocarbons, CFCs, have damaged it in the modern era, except that a GRB would deliver the energy far more rapidly and more uniformly across the hemisphere facing the burst. The calculation of ozone depletion from a GRB was worked out in detail by Brian Thomas and colleagues at Washburn University in a series of papers beginning in 2005. The key finding: a GRB within approximately 2 kiloparsecs, about 6,500 light-years, of Earth, with its jet pointed at us, would deplete the ozone layer over the illuminated hemisphere by 35 to 90%, depending on the specific burst energy and duration. Even a depletion of 35% would dramatically increase the UV flux reaching the surface. A depletion of 90% would be catastrophic. The timescale of ozone recovery matters enormously. Once the nitrogen oxide catalysts are produced in the stratosphere, they persist for years, slowly being removed by chemical reactions and transported to the troposphere, where they are washed out by rain. The ozone layer, once severely depleted, would take approximately 3 to 5 years to recover to near normal levels. During those years, the UV flux at the surface would be elevated, not uniformly, because the distribution of ozone depletion varies with latitude and atmospheric dynamics, but severely elevated at many locations. The hemisphere facing the burst at the moment of the event would suffer the most severe depletion. The far hemisphere would be initially shielded, but would experience secondary effects as nitrogen oxides are transported globally by stratospheric circulation. What does sustained elevated UV do to the biosphere? The effects are layered and cascade through ecosystems in specific ways. Marine phytoplankton, the microscopic photosynthetic organisms that form the base of marine food webs and that produce approximately half of Earth's oxygen, are particularly UV sensitive. Phytoplankton live in the upper, sunlit layers of the ocean and cannot shield themselves from surface UV by retreating to depth without losing access to the sunlight they need for photosynthesis. A sustained UV increase of the magnitude associated with a major ozone depletion event would cause large-scale mortality in phytoplankton populations, collapsing the productivity of the marine ecosystem from the bottom up. Fish populations, marine mammals, seabirds, everything that depends on the marine food web, would be affected through trophic collapse, not by direct UV damage. On land, the primary UV-sensitive targets are the actively dividing cells of plants, particularly in leaves and in the growing tips where cell division is most rapid. Elevated UV damages DNA in plant cells, causes leaf damage, and reduces photosynthesis efficiency. The agricultural impact would depend on the severity and duration of ozone depletion, but even modest sustained UV increases cause measurable reductions in crop yield for many staple crops including wheat, rice, and soybeans. A severe, multi-year ozone depletion would represent an agricultural crisis of unprecedented scale. the nitrogen oxide compounds produced in the stratosphere eventually descend to the troposphere, where they contribute to acid rain, nitric acid formation from dissolved NO2, causing additional damage to terrestrial and freshwater ecosystems, leaching nutrients from soils and acidifying freshwater systems on which many species depend. There are also secondary climatic effects. Ozone itself is a greenhouse gas and a significant absorber of incoming solar radiation at UV wavelengths. A global reduction in stratospheric ozone would alter the thermal structure of the stratosphere, affecting the large-scale atmospheric circulation patterns, the jet streams, the Hadley cells, the stratospheric winter polar vortex, that drive Earth's weather. Climate modeling of post-GRB scenarios is in its early stages, but the secondary effects on global temperature distribution and precipitation patterns could persist for years to decades after the initial event, compounding the direct biological damage. At closer distances, within a few hundred light years, additional mechanisms become significant. The prompt gamma rays themselves would deliver lethal or near-lethal radiation doses to organisms on the illuminated hemisphere, but this effect requires proximity that is extremely unlikely for events in our galaxy. More relevantly, the X-ray afterglow, which persists for days to weeks at high flux levels from a nearby burst, would add additional ionizing radiation to the atmosphere following the initial event, extending the ozone-depleting nitrogen oxide production beyond the initial burst duration. And at very close distances, within tens of light years, which is effectively impossible for a long GRB given the environments they require. The direct thermal and radiation effects would be lethal even through the atmospheric shielding. Chapter 5. GRB 221009A. The Boat and What It Taught Us. On October 9th, 2022, Earth was struck by the most energetic gamma-ray burst ever recorded. GRB 221009A was detected by the Fermi Gamma Ray Space Telescope and the Neil Gehrels Swift Observatory at approximately 1317 UTC. The burst was so bright that the Fermi GBM Gamma Ray Burst Monitor detector, designed to measure bursts with a wide dynamic range, saturated within the first second of observation. The LAT instrument on Fermi, which detects higher energy photons, took several hundred seconds to begin detecting the burst because the initial flux overwhelmed its dead time recovery. The Swift XRT, designed for exactly this kind of observation, also saturated in multiple energy bands. Integral, a European gamma-ray observatory, detected the event from a different orbital position and provided partially complementary data that helped reconstruct the total fluence. Multiple other gamma-ray and X-ray observatories confirmed the detection. On the ground, ionospheric monitoring stations around the world detected the effect of the gamma-ray burst on the ionosphere, specifically, an increase in the ionization of the D layer of the ionosphere, normally only affected during daylight hours by solar UV that was measurable even on the night side of Earth. The ionospheric disturbance from a source 2.4 billion light-years away was detectable on Earth's night side. This is an extraordinary statement. Gamma-ray bursts can physically alter Earth's atmospheric electrical properties from cosmological distances. The ionospheric disturbance caused by GRB 221009A deserves elaboration because it makes concrete, in a way that energy numbers alone cannot, the scale of what happened. Earth's ionosphere, the electrically charged upper atmosphere from about 60 to 1,000 kilometers altitude, is normally ionized during daylight hours by solar, ultraviolet, and X-ray radiation. On the night side, this solar ionization ceases, and the lower ionosphere, the D layer from about 60 to 90 kilometers altitude, largely recombines to neutral molecules. The boundary between the solar ionized day side and the neutral molecule night side is physically sharp. GRB 221009. A changed this on the night side of Earth. Ground-based very low-frequency radio stations, which use the ionosphere as a reflector for long-range communications, detected anomalous reflections from the night side ionosphere at the moment of the gamma ray burst. The D layer was being ionized not by sunlight, but by gamma rays from a source 2.4 billion light-years away. The effect was comparable to, and in some regions stronger than, a moderate solar X-ray flare. The gamma ray burst from across a significant fraction of the observable universe, delivered more ionizing flux to Earth's night side in a few seconds than many solar events do in hours. And this was a source at cosmological distance, with most of its energy beamed away from us. We were not in the jet. We were in the wings of the beaming cone, receiving only a tiny fraction of the total released energy. If we had been in the jet, Earth would not have had an ionosphere to measure. The source was subsequently localized and identified as lying in the direction of the constellation Sagitta at a redshift of Z equals 0.151, corresponding to a distance of approximately 2.4 billion light-years. The isotropic equivalent energy in gamma rays was calculated to be approximately 10 to the power of 54 joules, the largest ever measured for any GRB by roughly an order of magnitude above the previous record holders. Even correcting for beaming, the true energy release was extraordinary. The afterglow of GRB 221009A was detectable across the electromagnetic spectrum for months. High-energy photons, in the TeV range, the highest energy photons ever detected from a GRB, were observed by the Large High-Altitude Air Shower Observatory, LHAASO, in China, the first detection of tera-electron volt emission from a gamma-ray burst. The detection required these extreme energy photons to travel 2.4 billion light-years through the extragalactic background light, a diffuse sea of photons filling the universe produced by all past stellar and galactic activity, without being completely absorbed. The fact that TeV photons arrived at all from this distance imposes interesting constraints on the extragalactic background light density and on any exotic physics that might cause photon absorption at very high energies. The boat also provided new constraints on fundamental physics. Very high energy photons traveling cosmological distances can be affected by hypothetical effects of quantum gravity. Some theories of quantum gravity predict that the speed of light should be energy dependent at extreme energies, causing high energy photons to arrive earlier or later than lower energy photons from the same event. The LHAASO observations of TeV photons from GRB 221009A, with no observed energy-dependent time delay relative to lower energy photons, constrained the quantum gravity energy scale to be above 10 times the Planck energy, a significant constraint on Lorentz invariance violation that rules out some theoretical models. The boat was the most energetic GRB ever recorded, but most energetic ever recorded, requires interpretation. The observational record of GRBs extends back about 55 years, and the all-sky coverage of GRB detecting satellites means that most sufficiently bright bursts from any direction are captured. But the sample of detected bursts is still finite. There have been roughly 10,000 to 12,000 detected GRBs in the full historical record. The question of how the boat fits into the true distribution of GRB energies, whether it is a 1 in 10,000 year event or a 1 in a million year event, depends on the statistical modeling of the energy distribution, which has significant uncertainty. What is clear from the boat is that the upper end of the GRB energy distribution, the events that would be most dangerous to a biosphere within their effective range, extends to energies that were previously only inferred from theoretical models. The most energetic bursts in the observed sample are more energetic than the median burst by factors of 100 or more. And the distribution has no sharp upper cutoff at the observed energies. Events significantly more energetic than the boat are not ruled out. They would simply be rarer and would therefore require an even larger observational sample to detect. Chapter 6. The Galactic Rate. How often does this happen? The question of whether gamma-ray bursts represent a meaningful threat to life on Earth depends critically on the rate of GRBs within our own galaxy. The observed rate from the full sky surveys, 1 to 2 per day across the observable universe, is dominated by events in distant galaxies, not in the Milky Way. The relevant question is, how frequently do gamma-ray bursts occur in the Milky Way specifically, and what fraction of those are pointed at Earth? Estimating the galactic GRB rate is not straightforward because we have never directly observed a GRB in the Milky Way at close range. If one had occurred in the last few thousand years, it would have been the most spectacular astronomical event in recorded human history, and we would know about it. The absence of a recorded nearby GRB constrains, but does not eliminate the possibility of one having occurred in the past. The rate estimate proceeds from the observed cosmological GRB rate and the properties of host galaxies. Long GRBs preferentially occur in low metallicity, actively star-forming galaxies. The metal-poor environment is important because massive, rapidly rotating stars that can produce GRBs are more common when metallicity is low. High metallicity leads to stronger stellar winds, which carry away more of the star's angular momentum before death, making the rapidly rotating progenitor needed for jet formation less common. The Milky Way has a metallicity typical of a large spiral galaxy, not particularly low, which suggests the GRB rate here is lower than in the lower metallicity dwarf galaxies that dominate the long GRB host galaxy sample. The current best estimates for the long GRB rate in the Milky Way range from roughly 1 per 100,000 years to 1 per million years, with significant uncertainty. Short GRBs from neutron star mergers occur at a somewhat higher rate in large galaxies, like the Milky Way, but their energy per event is typically lower by a factor of 10 to 100, reducing their effective dangerous range. The next factor is beaming. A GRB only poses a danger if its jet is pointed at Earth. The jets of long GRBs have opening half angles of approximately 3 to 10 degrees. A jet with a half-opening angle of 5 degrees subtends a solid angle of approximately pi times 5 over 57.3 squared steradians, which is about 0.024 steradians, about 0.19% of the total sphere. For a burst pointed in a random direction, the probability of the jet intersecting Earth is roughly 0.1 to 0.2%. The rate of dangerous, that is, Earth-directed GRBs in the Milky Way is therefore roughly 1 per 50 million to 1 per 500 million years. From long GRBs alone, before any further adjustment for distance. But distance matters. Even a GRB in the Milky Way that is not pointing at Earth is not a threat. Only bursts within some maximum dangerous distance and pointing at Earth are relevant. Estimates of the dangerous range, within which a GRB would cause sufficient ozone depletion to be biologically significant, cluster around 1 to 3 kiloparsecs, 3,000 to 10,000 light-years, depending on assumptions about burst energy and atmospheric chemistry. The fraction of the galaxy's volume within this range of Earth is relatively small. The Milky Way extends to roughly 15 kiloparsecs in radius from the galactic center, so the relevant subset of potential GRBs is further reduced. Combining the galactic rate, the beaming fraction, and the dangerous distance range, the overall rate of genuinely Earth-threatening GRBs, those that would cause significant ozone depletion affecting the biosphere, is estimated at approximately 1 per 500 million years to 1 per billion years. This is a low rate over human historical timescales, but over the timescales of geological and biological evolution, hundreds of millions to billions of years. At least one and possibly several such events might have occurred in Earth's history. There is a specific observational hint that one might have. The Ordovician Silurian mass extinction, approximately 443 million years ago, is one of the largest mass extinctions in Earth's history. It eliminated about 85% of marine species. The extinction has a pattern that has puzzled paleontologists for decades. It appears to have occurred in 2 distinct pulses, and it was associated with a glaciation event. However, the specific pattern of extinction, with preferential loss of shallow water marine species, particularly those living in well-oxygenated surface waters, and relative survival of deeper water species, is consistent with what would be expected from a major ozone depletion event causing elevated UV flux at the ocean surface. The coincidence of timing and pattern is suggestive but not conclusive. A GRB in the Milky Way could have triggered this extinction without leaving an unambiguous geological trace, because the gamma ray burst itself deposits no extraterrestrial material. Unlike an asteroid impact, it leaves no iridium layer, no spheral horizon, no shocked quartz. The only record would be the biological pattern of the extinction itself. The GRB hypothesis for the Ordovician extinction was proposed by Mellott and colleagues in a 2004 paper in the International Journal of Astrobiology, and has been a recurring topic in astrobiology literature since. It is not the consensus explanation for the Ordovician extinction. Glaciation driven by the spread of land plants into new environments and the consequent drawdown of atmospheric CO2 is the most widely accepted primary cause. But the possibility that a GRB contributed to or triggered one of the big 5 mass extinctions is taken seriously enough by researchers that it appears in peer-reviewed discussions of the event. Chapter 7. The long GRB environments. Where they happen and why it matters. The distribution of long gamma-ray bursts across cosmic time and across galaxy types carries important information not just about the bursts themselves, but about the habitability of the universe, about where in the cosmos life is most and least threatened by these events. Long GRBs are not uniformly distributed across cosmic time. The observed rate of long GRBs per unit moving volume peaks at a redshift of approximately z equals 2, corresponding to a cosmic age of roughly 3 billion years after the Big Bang, the epoch of peak star formation rate in the universe. This makes sense. Long GRBs are produced by massive stars, and the rate of massive star formation tracks the overall star formation rate. In the early universe, when star formation was most intense and galaxy metallicities were lower, long GRB production was far higher than in the present epoch. This has a specific implication for the history of life in the universe. In the early universe, the first few billion years, the rate of long GRBs per galaxy was much higher than it is today. If life was attempting to develop on planets in young, actively star-forming galaxies 10 to 12 billion years ago, it would have been doing so in an environment with a GRB rate several times higher than the current Milky Way rate, in galaxies with lower metallicities that are intrinsically more prolific GRB producers. The early universe may have been significantly more hostile to the persistence of complex biospheres than the present epoch is. The role of metallicity is particularly important for assessing which regions of the present galaxy are most at risk. The galactic center, the innermost kiloparsecs of the Milky Way, has higher metallicity than the outer disk because it has been forming stars for longer and has been chemically enriched by more generations of stellar nucleosynthesis. Paradoxically, this means the galactic center, despite its higher stellar density, may actually produce fewer long GRBs per unit volume than the outer disk, because the high metallicity of its stars suppresses GRB production through the angular momentum stripping mechanism we discussed earlier. The outer disk and the outer halo, lower metallicity, but also lower star formation rate, present a different risk profile. Lower metallicity means higher GRB probability per massive star death, but fewer massive stars forming overall. The net effect is that the GRB rate per unit volume is not dramatically concentrated in any one part of the galaxy. The specific location of the solar system within the Milky Way matters in another way. The Sun sits at approximately 8 kiloparsecs from the galactic center in the relatively quiescent outer disk of a large spiral galaxy with above-average metallicity for the present cosmic epoch. This location, away from the intense star formation and high GRB production environments of compact starburst galaxies and galactic centers. In a galaxy whose metallicity suppresses GRB production, is one of the reasons that astronomers have argued the solar system's location within the Milky Way may itself be a factor in Earth's habitability. The galactic habitable zone concept, the idea that there is a range of galactocentric distances within which the combination of available heavy elements for rocky planet formation and low GRB and supernova rate for biosphere persistence optimizes the conditions for life, places Earth's current location within this zone. The galactic habitable zone concept is not universally accepted. It depends on specific assumptions about the galactic distribution of supernovae, GRBs, and stellar metallicity that have significant uncertainties. But the underlying physics is sound. The rate of ionizing radiation events of sufficient intensity to damage a planetary biosphere varies with location within the galaxy, and not all galactic environments are equally hospitable to the persistence of complex life. Chapter 8: The Physics of the Jet. Why they're so extreme. The physical mechanism that produces a gamma-ray burst jet is one of the most extreme fluid dynamics problems in astrophysics, and understanding it makes the energy numbers more vivid and the process more strange. When the central engine, the newborn black hole and its accretion disk, begins launching the jet, it does so by converting the gravitational and rotational energy of the infalling material and the spinning black hole into directed kinetic energy of the outflow. The jet is not powered by nuclear fusion. It is powered by two mechanisms: the extraction of rotational energy from the spinning black hole through magnetic fields, the Blandford-Znajek mechanism, first described in 1977 by Roger Blandford and Roman Znajek, and the energy deposition by neutrino-antineutrino annihilation in the funnel region above the accretion disk poles. Both mechanisms deposit energy preferentially along the rotation axis in a narrow cone. The jet material starts out opaque. It is so dense and energetic that photons cannot escape, so the energy propagates as bulk kinetic energy of the plasma rather than as radiation. As the jet material expands outward from the central engine, the density decreases, and at some characteristic radius, the photospheric radius, the jet becomes optically thin and photons can escape. This is one of the mechanisms proposed for the prompt gamma-ray emission. The Lorentz factors achieved by GRB jets, 100 to 1000, are the highest bulk velocities of any macroscopic objects in the universe. For comparison, the jets of active galactic nuclei, the relativistic jets from supermassive black holes at the centers of radiogalaxies and quasars, achieve Lorentz factors of typically 5 to 30. Pulsar jets and supernova ejecta are much slower. Only GRB jets routinely achieve Lorentz factors above 100. At a Lorentz factor of 100, the jet material is moving at 99.995% of the speed of light. The relativistic effects are extreme. Time dilation, length contraction, and relativistic beaming all combine to make the observed properties of the jet dramatically different from what they would be in the rest frame of the emitting material. The most counterintuitive consequence of the high Lorentz factor is relativistic beaming. The radiation emitted by a source moving toward the observer at a high Lorentz factor is concentrated into a narrow cone in the direction of motion, with a half angle of approximately 1 over gamma radians, where gamma is the Lorentz factor. For gamma equals 100, this beaming cone has a half angle of 0.6 degrees. The radiation that in the rest frame of the emitting material would be emitted in all directions is, in the observer's frame, compressed into a tiny fraction of the sky directly ahead of the jet. This is why GRBs appear so bright to observers who happen to be within the beaming cone. They are receiving radiation that in the emitting frame was spread over a much wider solid angle, but has been compressed and boosted in energy by the relativistic motion of the source. The temporal structure of GRB emission is extraordinarily complex and is one of the outstanding unsolved problems in GRB physics. A typical long GRB light curve, the plot of gamma ray flux versus time, shows multiple overlapping pulses with rise times of milliseconds and decay times of hundreds of milliseconds superimposed on a smoothly varying envelope. The millisecond variability implies that the emitting region must be smaller than a light millisecond, about 300 kilometers, because information cannot propagate faster than the speed of light. A region 300 kilometers across, containing all the energy being released, collimated into a beam moving at 99.999% of the speed of light. The physical conditions inside the emitting region, magnetic field strengths, particle densities, temperatures, are incomprehensible by any ordinary scale. Magnetic fields potentially exceeding 10 to the 12th power Gauss. Electron energies of billions of electron volts. Photon densities so high that two photons can collide and produce an electron-positron pair. Inside a GRB jet, matter and energy are interchangeable in the most literal sense. The photon flux is so intense that photons are constantly producing pairs of electrons and positrons, and those pairs are annihilating back into photons. The jet is a boiling mixture of radiation and relativistic plasma, confined by its own inertia, expanding outward from a black hole at a velocity that makes the most energetic particles ever produced in the LHC look leisurely. Chapter 9: Multi-Messenger Astronomy. Reading the same event in every language. One of the most profound changes in astrophysics over the last decade has been the shift from single-channel observation, looking at the universe in one wavelength range with one kind of detector, to multi-messenger observation, in which the same event is read simultaneously in light across all wavelengths, in gravitational waves, in neutrinos, and in cosmic rays. Gamma-ray bursts have been at the forefront of this transition because they are one of the few categories of astrophysical event that produces detectable signals in multiple messengers simultaneously. The paradigm event in this transition was GW 170817 on August 17, 2017. Two neutron stars spiraled together and merged at a distance of approximately 130 million light-years, relatively close by extragalactic standards. The gravitational wave signal was detected by the LIGO detectors in Hanford, Washington, and Livingston, Louisiana, and by the Virgo detector near Pisa, Italy. 1.74 seconds after the merger signal, a short gamma-ray burst was detected by the Fermi GBM and the Integral satellite. The time: delay of 1.74 seconds between the gravitational wave, merger signal and the gamma-ray signal is physically meaningful. It represents the travel time for the relativistic jet to break free from the merger environment and begin emitting gamma rays, combined with any intrinsic delay between the merger and jet launch. The 1.74 second delay is consistent with theoretical models of jet formation from neutron star mergers and provides constraints on the timescale of post-merger accretion disk evolution. The power of the combined gravitational wave and gamma-ray detection for GW 170817 extended far beyond simply confirming that neutron star mergers produce short GRBs. The same 1.74 second delay constrained the speed of gravity relative to the speed of light to within 1 part in 10 to the 15th power. The tightest limit ever placed on this ratio, eliminating entire classes of modified gravity theories that had been proposed to explain the accelerating expansion of the universe without dark energy. The gravitational waves and the photons arrived within 1.74 seconds of each other after a journey of 130 million light-years. If gravity and light traveled at even slightly different speeds, the delay would have been measurable over that distance. They did not. The speed of gravity is equal to the speed of light to extraordinary precision, and GW 170817's combined detection is how we know. GRB 221009A, the boat, added another dimension to multi-messenger GRB astronomy through the LHAASO detection of very high-energy gamma rays. The Large High-Altitude Air Shower Observatory in Sichuan, China, is a ground-based detector array that measures the particle showers produced when very high-energy gamma rays and cosmic rays strike Earth's upper atmosphere. When a TeV energy photon enters the atmosphere, it produces a cascade of secondary particles, an air shower, that can be detected by the particle detectors and water Cherenkov detectors at LHOASO's altitude of 4,400 meters. The SINAB detection of photons up to approximately 18 teravolts from GRB 221009A represented a leap in the maximum photon energy ever detected from a GRB by more than an order of magnitude. These extreme energy photons carry specific information about the acceleration mechanisms within GRB jets, the conventional synchrotron and inverse Compton mechanisms that produce the prompt and afterglow emission from GRBs can produce photons up to the giga-electron-volt range relatively straightforwardly. Producing teravolt photons from a GRB requires either a more extreme version of these mechanisms operating in the afterglow, specifically synchrotron self-Compton emission in a regime of very high magnetic field and very high electron energy, or exotic acceleration processes beyond the standard models. The LHAASO TeV detection from the boat is still being actively analyzed, and its implications for GRB jet physics are not fully understood. But it demonstrated definitively that the photon energy range accessible from GRB extends far higher than previously observed, with implications for our understanding of the most energetic particle acceleration environments in the universe. Neutrino detection from GRBS has been a long-sought goal that has not yet been definitively achieved. GRB jets are expected to produce high-energy neutrinos through proton-photon interactions. Relativistic protons in the jet interact with the intense gamma-ray field to produce pions, which decay to muons and neutrinos. The IceCube Neutrino Observatory at the South Pole, a cubic kilometer of Antarctic ice instrumented with photodetectors to catch the Cherenkov light produced by high-energy neutrinos interacting with ice, has searched for neutrino emission correlated with GRBs without finding a statistically significant signal. The absence of a detection constrains the efficiency of proton acceleration within GRB jets. Either the protons are not accelerated to as high energies as some models predict, or the neutrino production efficiency is lower than expected, or both. The search continues with the eventual goal of detecting GRB neutrinos, providing direct insight into hadronic particle acceleration in the most extreme electromagnetic environments in the universe. The neutrino non-detection from GRBS is itself a major result that has fundamentally changed models of GRB jets. The original expectation, based on models from the late 1990s and early 2000s, was that GRB jets should be efficient accelerators of hadrons, protons, and heavier nuclei to ultra-high energies. If this were the case, the proton-photon interactions in the intense photon field of the GRB jet should produce pions copiously, and those pions should decay to produce neutrinos at a rate detectable by IceCube from even moderately distant bursts. IceCube searched for this signal across hundreds of bursts over more than a decade. Nothing was found at statistically significant levels. What does the non-detection mean? Either the proton acceleration in GRB jets is less efficient than the original models predicted. The jets are dominated by electromagnetic energy rather than hadronic energy. Or the gamma-ray emission region is located at larger radii from the central engine than the early models assumed, reducing the density of seed photons available for pion production. Or both. The neutrino non-detection from GRBs has been interpreted as evidence that GRBs are not the primary source of the ultra-high energy cosmic rays. The extremely energetic protons and heavier nuclei that arrive at Earth from extragalactic sources, and that IceCube was originally motivated to trace back to GRBs. If GRBs are not producing high-energy neutrinos efficiently, they are probably not accelerating the protons that become ultra-high-energy cosmic rays to the required energies. The source of the most energetic cosmic rays remains one of the major open questions in high-energy astrophysics, and the GRB non-detection has sent that search elsewhere, toward active galactic nuclei, starburst galaxies, and galaxy cluster shocks as alternative candidate sources. The IceCube Neutrino Observatory is currently operating at its design sensitivity, and the proposed IceCube Gen 2, a 10-fold expansion of the detector volume to roughly 10 cubic kilometers, would increase the neutrino detection sensitivity by approximately a factor of 5 for point source searches. If GRBs do produce neutrinos at a level below the current IceCube threshold, IceCube Gen 2 would have a realistic chance of detecting them over a multi-year observing campaign. A confirmed neutrino detection from a GRB would be transformative for our understanding of particle acceleration in these jets, and would provide a direct window on the hadronic physics occurring inside the relativistic outflow. The development of truly multi-messenger astronomy for GRBs, gravitational waves from the merger, gamma rays from the jet, optical/infrared emission from the kilonova, X-ray and radio afterglow from the decelerating jet, and eventually neutrinos from hadronic processes in the jet, will, over the coming decade, provide a complete physical picture of these events that no single observation channel can provide alone. The planned upgrades to LIGO, A+, and later upgrades, combined with the Einstein telescope and the Cosmic Explorer proposed for the 2030s, will increase the gravitational wave detection horizon for neutron star mergers by an order of magnitude, bringing events like GW 170817 within reach at distances of billions rather than hundreds of millions of light years. Combined with the next generation of gamma-ray observatories, including the proposed Amigo X and LEAP missions, The multi-messenger era for GRBs is only beginning. Chapter 10: Extreme GRBs. How powerful can they get? The boat established a new empirical upper bound on observed GRB energies, but the question of whether this represents a true physical upper limit, whether there are mechanisms that cap the energy a GRB can release, or merely the brightest event in a 55-year observational sample, is one of the most interesting open questions in the field. From a theoretical standpoint, there is no sharp upper limit on GRB energy. The energy budget of a GRB depends primarily on three factors: the mass of the central black hole, the mass and accretion rate of the surrounding disk, and the efficiency with which the Blandford-Znajek mechanism or neutrino annihilation extracts that energy into the jet. For a massive stellar progenitor, a star with initially 50 to 100 or more solar masses, the iron core that collapses to form the black hole can be several solar masses, and the remaining stellar envelope available to form the accretion disk can be tens of solar masses. In extreme cases, the most massive, most rapidly rotating progenitor stars, the accretion disk can sustain high accretion rates for longer, launching more powerful jets for longer durations. There is a class of hypothetical objects that would represent the upper extreme of GRB progenitors: the merger of two massive stars in a binary system just before they individually collapse, a scenario sometimes called a collapsar-collapsar merger, or the collapse of a supermassive star, a hypothetical object of thousands of solar masses proposed to explain the formation of the earliest supermassive black holes. If these more exotic progenitors exist and can produce GRBs, the energy upper limit could be significantly above the boat. Whether they occur in nature at rates high enough to be relevant to the observed GRB population is uncertain. There is also the question of ultra-long gamma-ray bursts, a subclass of long GRBs with durations of thousands of seconds, tens of minutes to hours, compared to the typical tens of seconds to minutes of ordinary long GRBs. A handful of events with durations exceeding 10,000 seconds have been detected, and their physical origin is debated. Some may represent a different class of progenitor altogether. The collapse of a blue supergiant star, which has a more extended envelope requiring more time for the jet to traverse, or possibly the tidal disruption of a star by an intermediate mass black hole. Ultra-long GRBs, if they represent a physically distinct class, with very high total energy output sustained over long durations, could produce significantly higher total fluences at a given distance than ordinary long GRBs. There is a third class of GRB central engine that is relevant to the extreme energy discussion: the millisecond magnetar. In the standard collapsar model, the central engine is a stellar mass black hole accreting from a disk. But in some models, particularly for short GRBs and for some long GRBs, the central engine may instead be a rapidly spinning, highly magnetized neutron star, a millisecond magnetar, born from the merger or from the core collapse. Millisecond magnetar with a surface magnetic field of 10 to the 15th power Gauss, spinning at 1,000 revolutions per second, contains an enormous reservoir of rotational energy, approximately 10 to the power of 53 ergs, that can be extracted over seconds to minutes by the magnetic field as it transfers angular momentum to the surrounding environment through electromagnetic torques. This is the millisecond magnetar engine model, and it can produce GRBs with energy outputs that rival or exceed those from black hole engines, with specific spectral and temporal signatures that differ from the black hole accretion disk model. The millisecond magnetar model is motivated partly by the discovery of extended emission in some short GRBs, gamma-ray emission that continues for tens of seconds after the initial short burst, when the merger remnant accretion disk should have been consumed. If the remnant is instead a millisecond magnetar, slowly spinning down and injecting energy into the surrounding environment, the extended emission is a natural consequence. The boat's extraordinary energy has been proposed in some analyses to be consistent with a magnetar central engine that was particularly energetic and long-lived, though a black hole engine with a massive accretion disk is equally consistent with the observations. The distinction between black hole and magnetar central engines matters for the threat question because the energy release timescale and spectral distribution are different. A magnetar engine, spinning down over minutes, produces a more sustained injection of hard radiation into the jet than a black hole engine drawing down a finite accretion disk. If the most dangerous GRBs have magnetar engines, the duration of the ionizing radiation dose delivered to a nearby planet's atmosphere is longer, potentially driving more complete ozone depletion before atmospheric chemistry can begin any recovery. This remains an open question in GRB physics, and the answer would affect threat calculations at dangerous distances. For the purposes of the threat question, the relevant scenario is not the most energetic possible GRB in the universe, but the most energetic plausible GRB in the Milky Way. What the upper tail of the energy distribution looks like for events occurring in a galaxy like ours. Given the current best estimates of the Milky Way GRB rate and the observed GRB energy distribution, the most energetic GRB that might occur in the Milky Way in the next billion years, the 99th percentile event, would likely have an isotropic equivalent energy somewhere in the range of 10 to the power of 53 to 10 to the power of 54 joules, and a true beaming-corrected energy of perhaps 10 to the power of 44 to 10 to the power of 45 joules. This is comparable to the boat and represents the realistic upper end of what the Milky Way might plausibly produce. The specific danger of a very energetic GRB close to Earth is worth spelling out numerically. A burst with a true gamma-ray energy of 10 to the power of 44 joules at a distance of 1,000 light-years and beamed directly at Earth would deliver an energy fluence of approximately 100 kilojoules per square meter to the top of Earth's atmosphere. For comparison, the total annual solar energy flux on Earth's surface is about 1,400 watts per square meter integrated over a year, or about 44 gigajoules per square meter per year. The GRB fluence of 100 kilojoules per square meter is negligible compared to annual solar energy. It is roughly equivalent to the solar flux over 1 minute. But the mechanism by which this fluence damages Earth has nothing to do with depositing significant heat. It is about chemistry, and specifically about the chemistry of nitrogen oxides at stratospheric altitudes, which is extraordinarily sensitive to gamma-ray fluence. The relevant threshold for significant ozone depletion is gamma-ray fluences of approximately 100 kilojoules per square meter, exactly in the range that a moderate GRB at a few hundred to a few thousand light-years would deliver. The biological impact is triggered by a fluence that is tiny in energy terms, but devastating in chemical terms. Chapter 11. The Threat Quantified. What dangerous actually means. Let us now be precise about what the threat from gamma-ray bursts actually is, and equally precise about what it is not. The threat is not extinction from direct energy deposition. No gamma-ray burst from anywhere outside our solar neighborhood could deliver enough raw energy to sterilize Earth in the way an asteroid impact or a nuclear war could. The energy fluences involved, even for the closest plausible GRBs, are too small to heat the Earth significantly or cause physical destruction at the planetary scale. What a GRB at dangerous distance does is not incinerate. It blinds. It strips the ozone layer, leaving the biosphere exposed to UV radiation from its own star for years, while the ozone slowly recovers. This distinction matters enormously for what kinds of life are most at risk. Organisms that live below UV shielding layers, in the ocean at moderate depths, underground, in dense forest understory, are relatively protected even during a severe ozone depletion event. Organisms that live at or near the surface in full UV exposure, phytoplankton in the sunlit ocean layer, terrestrial plants and animals in open environments, are most at risk. The extinction selectivity of a GRB-induced ozone depletion event is not random death. It is preferential elimination of UV-sensitive, surface-exposed organisms, with the knock-on effects cascading through food webs that depend on them. The specific biological vulnerability to UV radiation is itself complex and species-dependent. Some organisms have highly efficient DNA repair mechanisms or produce UV-absorbing compounds as natural sunscreens, mycosporin-like amino acids in corals and some phytoplankton species, melanin in terrestrial organisms, carotenoids in various photosynthetic organisms. These biochemical defenses reduce UV sensitivity but do not eliminate it. Over the multi-year period of elevated UV following a major ozone depletion event, even organisms with good UV defenses would experience elevated mutation rates, elevated energy costs of repair, and reduced reproductive success. Populations that could sustain normal reproductive rates under normal UV conditions would be stressed under the elevated post-GR-BUV environment, and population sizes would decline even without catastrophic acute mortality. The evidence from previous mass extinction events on Earth gives us some empirical grounding for what biosphere-scale UV damage looks like, though the evidence is necessarily indirect, and the GRB hypothesis for past extinctions is contested. The most comprehensive quantitative study of GRB threat to Earth was published by Malott, Thomas, and colleagues in a series of papers from 2004 to 2011 using atmospheric chemistry models, validated against observations of ozone depletion during actual geomagnetic storm events and solar energetic particle events. Their conclusion was consistent across different model assumptions. A GRB within approximately 2 kiloparsecs beamed at Earth with a typical energy for its class would cause ozone depletions of 35 to 90% over the directly illuminated hemisphere. At the high end of this range, the UVB flux at Earth's surface would increase by a factor of approximately 50 to 100, far beyond any biologically survivable acute exposure for most surface organisms. A factor of 50 UVB increase for 3 to 5 years is not a recoverable perturbation for most surface marine and terrestrial ecosystems. It is a mass extinction event, not because every individual organism dies immediately, but because the foundation species, the photosynthesizers at the base of the food web, are sufficiently damaged that the cascading loss of productivity through the trophic levels leaves most higher-order consumers without adequate food resources. The selectivity of the extinction, heavy losses among surface-dwelling marine invertebrates and photosynthetic organisms, relative survival among deeper water and underground species, is, as noted, consistent with the observed pattern of the Ordovician extinction. There is a refinement to the threat calculation that is important. The question of which hemisphere is facing the GRB at the moment of the burst. The prompt gamma ray emission from a GRB is received essentially instantaneously. It arrives at the speed of light, and the duration of the burst, seconds to minutes, means that the hemisphere facing the burst receives the full fluence, while the far hemisphere receives essentially none during the prompt phase. The ozone depletion in the directly illuminated hemisphere will therefore be severe and immediate, while the far hemisphere is initially spared. However, stratospheric circulation, the global transport of air masses at stratospheric altitudes, will eventually distribute the nitrogen oxide compounds around the globe. On timescales of weeks to months, the ozone-depleting chemicals spread from the illuminated hemisphere to the far hemisphere, producing ozone depletion at all latitudes, though less severe at the latitudes that were initially shielded. By the end of the first year, the ozone depletion is global. It is just more severe in the hemisphere that was facing the burst. The recovery of the ozone layer after the nitrogen oxide injection also has a spatial structure. Ozone recovery depends on the photochemical reactions that remove nitrogen oxide compounds from the stratosphere, and these reactions are driven by sunlight. They proceed faster in the tropical stratosphere and slower at high latitudes. The recovery timescale therefore varies with latitude, with polar regions potentially experiencing longer-lasting ozone depletion than the tropics. The coldest, darkest, most remote environments on Earth, the deep ocean, deep soil, cave systems, are the most resistant to the effects of a GRB event. Life in these environments would continue largely unaffected by the UV crisis at the surface, and could serve as refugia from which the biosphere would eventually recover and repopulate the surface. This is not unique to GRBs. It is the general pattern of mass extinction and recovery on Earth, where the deepest and most isolated life forms tend to survive events that eliminate most of the surface biosphere. After the Chicxulub impact, the oceanic and soil communities recovered and eventually diversified to refill the ecological vacancies left by the mass extinction. A GRB-induced extinction would follow the same recovery trajectory, driven by survivors in refugia over millions of years. To put the threat in a broader quantitative context, it helps to compare the GRB threat rate to other existential and civilization-level threats on similar timescales. The impact probability of a 10-kilometer asteroid, the class that caused the Chicxulub extinction event, is approximately 1 per 100 million years, based on the known population of near-Earth objects and their impact cross-sections. This is roughly comparable to the estimate for genuinely Earth-threatening GRBs of 1 per 500 million to 1 per billion years. GRBs are, by this comparison, perhaps 5 to 10 times less frequent per unit time than large asteroid impacts in terms of extinction-causing events. But the uncertainty ranges overlap significantly, and the comparison depends on specific definitions of extinction-causing for both categories. Compared to other stellar explosion threats, GRBs are less frequent than the risk from nearby supernovae. A core collapse supernova within about 8 parsecs, roughly 25 light-years, would deliver sufficient X-ray and gamma radiation to cause significant ozone depletion. The rate of such nearby supernovae is estimated at roughly 1 per 300 million years. But the ozone depletion from a nearby supernova would be less severe than from a GRB at a somewhat greater distance. The supernova emits radiation isotropically without the beaming factor that concentrates GRB energy, and the total energy in ionizing radiation is lower for a supernova than for a GRB at its dangerous distance. The GRB is the more catastrophic individual event, but the rarer one. Magnetars, strongly magnetized neutron stars that occasionally release enormous bursts of soft gamma radiation in giant flares, are another relevant category. The Milky Way contains an estimated 10 to 30 magnetars, and giant flares from extragalactic magnetars have been observed at distances of tens of millions of light-years. A giant flare from a Milky Way magnetar at close range could potentially cause ozone depletion, though the energy released is typically several orders of magnitude less than a GRB. The threat from magnetar giant flares is generally considered less severe than from GRBs, but the frequency of such events within the galaxy is higher because magnetars are numerous compared to the rate of GRB-producing stellar collapses. The overall picture that emerges from comparing these different categories of high-energy astrophysical threats is that Earth's biosphere is exposed to a diversity of radiation-induced ozone depletion risks on geological timescales, of which GRBs represent the rarest and potentially most severe category. The Earth has survived billions of years of this exposure, suggesting either that the rate is low enough that major events have been genuinely rare, or that the biosphere has repeatedly recovered from damaging events without leaving unambiguous records, or both. There is one scenario that is genuinely more severe than the single GRB impact. A GRB occurring when Earth's other defenses are already weakened. Earth's magnetic field strength has varied significantly over geological history, and it is currently in a secular declining phase. The field is measurably weaker than it was a few centuries ago, and the South Atlantic anomaly represents a region where the field is particularly weak. A weak magnetic field provides less protection against cosmic ray bombardment, slightly increasing the baseline rate of DNA damage in organisms. Combined with a GRB event, the elevated cosmic ray flux through a weakened magnetic field would compound the UV damage from ozone depletion. The two effects together, elevated surface UV from ozone depletion and elevated cosmic ray flux through a weakened magnetosphere, would be more biologically damaging than either alone. This is not a reason for imminent alarm, but it is a reason why the risk from GRBs is not entirely independent of Earth's internal geophysical state. Chapter 12. The Fermi Paradox Connection. Are GRBs filtering life? Everything discussed so far has been about what a GRB would do to Earth specifically, but GRBs are not unique to the Milky Way, and the question of their biological impact extends to the broader question of whether gamma-ray bursts represent a significant filter on the development of complex life anywhere in the universe. This is the connection between GRB science and the Fermi paradox. The question of why, given the enormous number of potentially habitable worlds in the universe, we have not detected any evidence of other intelligent civilizations. Among the many proposed great filter mechanisms, the steps in the development from simple chemistry to galaxy-spanning civilization that are so improbable as to explain the apparent absence of detectable alien life. GRBs have been seriously proposed as a component. The argument was formalized most rigorously in a 2014 paper by Piran and Jimenez in Physical Review Letters, titled Possible Role of Gamma-Ray Bursts on Life Extinction in the Universe. Their analysis began from the observed GRB rate as a function of redshift and metallicity, and asked, what fraction of stars in the observable universe have been exposed to a GRB of sufficient energy to cause a major sterilization event, defined as affluence above the threshold for severe ozone depletion, within the last billion years? The Piran-Jimenez result was striking. The GRB rate in the early universe, the first few billion years after the Big Bang, was so high, and the prevalence of low metallicity star-forming environments so widespread, that essentially the entire universe in the first few billion years was hostile to the persistence of complex biospheres. The GRB rate was too high for any planet to go a billion years without being hit by a damaging event. Complex multicellular life requires approximately hundreds of millions of years of evolutionary development from simpler precursors, time that was not available if the biosphere resetting events from GRBs were occurring every few 100 million years or more frequently. The calculation had a specific implication for the timing of life's emergence in the universe. Below a redshift of approximately z equals 0.5, corresponding to a cosmic age of about 9 billion years, roughly 5 billion years ago, the combination of lower GRB rate and higher metallicity in established large spiral galaxies begins to create environments where the GRB threat is low enough for complex life to potentially persist. The Milky Way at its current position in cosmic history, a mature, high metallicity, large spiral galaxy in a universe where the star formation rate has declined significantly from its peak, is, by this analysis, in one of the less GRB hostile environments in the current universe. The Piran-Jimenez analysis also found a strong dependence of GRB threat on galactocentric distance. In the current universe, star-forming regions close to galactic centers, particularly in compact starburst galaxies and in the dense inner regions of large spirals, have the highest GRB rates. Planets in these environments are far more likely to experience damaging GRB events than planets in the outer disks of large quiescent spiral galaxies at the current epoch. If this analysis is correct, the galactic habitable zone is not merely a concept defined by available metallicity for rocky planet formation. It is also defined by the GRB rate, which disfavors intergalactic regions. The most striking implication of the Piran-Jimenez analysis, the one that has attracted the most discussion in astrobiology, is what it implies about the timing of intelligent life in the universe. If the GRB environment in the early universe was hostile enough to prevent complex biospheres from persisting for the hundreds of millions of years needed to develop multicellular complexity, then intelligent life cannot have arisen anywhere in the universe in the first 5 to 6 billion years after the Big Bang. The universe was simply too violent. This places a minimum age on any civilization in the observable universe. They cannot be older than about 8 to 9 billion years, the cosmic age at which galactic environments began to be calm enough for complex life to persist. Since the universe is 13.8 billion years old, this means the window for intelligent life is at most 5 to 6 billion years wide. Earth's own civilization arose at the very end of this window, about 0.3 million years ago, in a universe 13.8 billion years old. We are not exceptionally early. We are not in the first generation of possible civilizations. We may be in the first few generations, but the window has been open for 5 to 6 billion years, not for just a few hundred million. If the window has been open for 5 to 6 billion years, and if Earth-like planets around Sun-like and K-dwarf stars in appropriate galactic environments are common enough that complex life has had multiple opportunities to arise elsewhere in the galaxy, then the Piran-Jimenez analysis shifts the Fermi paradox question rather than resolves it. GRBS may have delayed the emergence of complex life by several billion years relative to the age of the universe, but they do not eliminate the emergence of complex life in the last 5 billion years. Within that remaining window, the galaxy has had ample time for many independent origins of complex life, if the per-planet probability is non-negligible. The silence of the galaxy, the absence of detectable signatures of other civilizations, must then be explained by something other than GRBs alone. What GRBs may contribute to the Fermi paradox is a more subtle filter, not the prevention of life's origin, but the periodic resetting of biospheres that are making progress toward complexity. A planet that has developed complex multicellular life over 500 million years of evolution, and then suffers a GRB-induced mass extinction that resets it to a simpler state, must start the clock again. If GRBs occur frequently enough relative to the evolutionary timescale needed to reach intelligence, the expected time from life's origin to intelligence becomes much longer than the unperturbed calculation would suggest. The required timescale to reach intelligence may be not just 4 billion years, but 4 billion years, plus the time lost to GRB-induced resets. And if resets occur every few hundred million years on many inhabited planets, a significant fraction may never reach intelligence within the available cosmic time. The Piran-Jimenez result is not without critics. The calculation depends on the GRB rate at different redshifts, the metallicity dependence of GRB rate, the assumed dangerous fluence threshold, and the assumed ozone depletion and recovery models, each of which has uncertainties. Subsequent analyses by other groups have found more or less severe constraints depending on the specific assumptions. Some analyses suggest that the GRB constraint on life is so severe that complex life in the observable universe is restricted to the last 5 billion years and to within the outer regions of large, metal-rich galaxies. Others find less extreme constraints, suggesting that GRBs are a significant but not dominant filter on complex life. The debate remains active. What is not in dispute is that GRBs are a real, recurring, galaxy-wide threat to planetary biospheres, with a rate that varies predictably with metallicity, star formation rate, and galactic position. They are not hypothetical. They are observed, cataloged, and physically understood at a level of detail sufficient to make quantitative predictions about their biological impact. Whether GRBs represent the dominant filter in the Fermi paradox, or merely a contributing factor alongside other threats, like supernovae, asteroid impacts, and planetary processes, depends on exactly where in the distribution of galactic environments a given planet sits. For Earth specifically, the analysis places our planet in a relatively favorable position in the outer disk of a high metallicity large spiral galaxy in an epoch when the universe's overall GRB rate has declined from its peak, at a galactocentric distance that minimizes exposure to the highest rate star-forming environments. Whether this favorable position is the result of some form of selection pressure. Life only arose here because it is the kind of place where complex life can persist, or simply coincidence, or some combination, is a question that touches the deepest issues of the anthropic principle and the distribution of life in the universe. What the Fermi paradox connection makes clear is that GRBs are not merely spectacular astronomical events of academic interest. They are, in the current scientific understanding, one of the primary environmental forces shaping the distribution of life in the universe across cosmic time. They define, in a very real sense, where and when life can exist, not where it can originate necessarily, but where it can persist long enough to become complex. Conclusion: the honest accounting. Let us be honest about what we know and about what we don't. We know that gamma-ray bursts are the most energetic events in the universe since the Big Bang. We have observed this, not inferred it, not calculated it theoretically, observed it in over 10,000 events detected across 55 years of monitoring. We know the energy scales, the rates, the progenitor mechanisms, and the physical processes involved in sufficient detail to make quantitative predictions about their effects. We know that a gamma ray burst within a few thousand light-years of Earth, with its jet pointed at us, would cause a severe and prolonged depletion of the ozone layer, with cascading biological consequences that amount to a mass extinction event. This conclusion is based on atmospheric chemistry models, validated against observed ozone depletion events, applied to the specific energy inputs from GRBs. It is not speculative. We know that the rate of genuinely Earth-threatening GRBs, those close enough, energetic enough, and pointed at Earth, is low enough that the expected time between events in our galaxy is measured in hundreds of millions to billions of years. Over Earth's 4.6 billion year history, at least one and possibly a few such events might have occurred. Whether any of the 5 major mass extinctions in Earth's history was caused or contributed to by a GRB cannot be established with certainty. GRBs leave no physical geological trace, but the biological patterns of at least one extinction, the Ordovician, are consistent with what a GRB would produce. We know that the boat, GRB 221009A, was the most energetic event of its kind ever recorded, that it came from 2.4 billion light-years away, that it was not in the Milky Way, and that despite this enormous distance, it measurably disturbed Earth's ionosphere and was detectable in dozens of observatories across the world. If the boat had occurred in the Milky Way, pointed at Earth, at a distance of a few thousand light-years, we would not be talking about ionospheric disturbances. We would be talking about ozone depletion on a planetary scale and a biological crisis that would rewrite the history of life on Earth. We know that the Milky Way is, by current best estimates, a relatively inhospitable environment for long GRBs compared to the lower metallicity dwarf galaxies and starburst environments where most observed bursts occur. Our location in a mature, high metallicity large spiral galaxy in an epoch of declining cosmic star formation rate places us in a less dangerous position than many planets in the universe at the current time, and in a vastly less dangerous position than planets in the early universe when GRB rates were far higher. What we do not know is whether we have been lucky, or whether the favorability of Earth's galactic environment is part of the reason complex life arose here at all. We do not know with certainty whether any past extinction event was caused or contributed to by a GRB, because GRBs are perfect criminals. They vanish without physical evidence, leaving only the consequences. And we do not know, this is the genuinely open question, what the upper limit of GRB energy is, how frequently boat-class events occur in a galaxy like ours, and whether the statistical models that give reassuring estimates of the dangerous event rate have correctly captured the tail of the distribution. The boat was, in the 55-year observational sample, approximately an order of magnitude more energetic than anything seen before. If the true rate of boat-class events is higher than the sample suggests, if we simply haven't been watching long enough to see how often they occur, then the tail risk is larger than the central estimates suggest. This is a standard problem in the statistics of rare extreme events. The most dangerous category is the one you have seen the fewest examples of. Let's make this concrete. Imagine GRB 221009A, the boat, had occurred not in a galaxy 2.4 billion light-years away, but in the Milky Way, 3,000 light-years from Earth, with its jet pointed directly at us. What would actually happen? First event, the gamma ray burst itself. The prompt emission, arriving at the speed of light with zero warning, would strike Earth's atmosphere over the course of approximately 300 seconds, the duration of the boat's prompt emission. From Earth's surface, nothing would be immediately visible or felt. The gamma rays deposit their energy in the stratosphere, not at the surface. The initial burst would ionize the ionosphere globally, disrupting radio communications and GPS systems. The gamma ray flux would be sufficient to produce measurable radiation doses at the surface, perhaps equivalent to a few medical X-rays over the duration of the burst, not immediately harmful to individuals, but detectable by dosimetry. The satellites in low Earth orbit would experience significant radiation damage, potentially ending the operational life of some. No thermal effect at the surface, no seismic effect. For most of humanity, the first hours and days would feel completely normal. The ozone chemistry begins immediately, but the consequences take months to years to become apparent at the surface. Within weeks, the UVB flux at the surface of the sunlit hemisphere would begin to climb. By 6 months, the ozone column in the directly affected hemisphere might be 60 to 90% depleted. The sunburn time on a clear day, the time to receive a sun-burning UV dose, would drop from 10 to 15 minutes in mid-latitude summer to perhaps 1 to 2 minutes. Outdoor activity in unprotected skin would become genuinely hazardous within months of the event. Agricultural production would fall as UV damage reduces crop yields. Marine fisheries would collapse progressively as phytoplankton populations collapsed. The food system impacts would be severe within a year or two of the event. Over 3 to 5 years, while the ozone slowly recovered, the cumulative impact on the biosphere would be comparable to a mass extinction event as measured on geological timescales. Not the end of humanity, but the end of many species, and the severe disruption of the food systems that support modern human civilization at its current scale. What should you take from all of this? Not a specific fear of a near-term gamma-ray burst. The rates are too low for individual human concern, and there is nothing we could currently do about a GRB even if we detected it in the early stages of its approach, because gamma rays travel at the speed of light and arrive at Earth at the same moment the event becomes detectable. You would not have warning. There is no planetary deflection strategy for a beam of light. What you should take from it is a sense of the true scale of what the universe is doing at every moment. Every day, somewhere in the observable universe, in some galaxy, in some corner of the cosmic web, a massive star collapses, or 2 neutron stars merge, and the result is an event so energetic that its light, diluted and redshifted across billions of light years, is still measurable in instruments on a small planet orbiting an unremarkable star in the outer arm of a spiral galaxy. Every day. The universe is not calm. It is not gentle. The peace we experience on the surface of this planet is a local, temporary arrangement, a narrow window of stability in a cosmos that casually produces events that dwarf everything our civilization has ever done, every second of every day, at distances so vast that most of what happens is invisible to us, even with our best instruments. But here is what I think is the most important thing the science of gamma-ray bursts tells us. And it is not about threat or catastrophe, it is about time. The Piran-Jimenez analysis suggests that complex life in the universe was effectively precluded for the first 5 billion years by the intensity of the GRB environment. The early universe was too violent, too full of short-lived massive stars exploding and merging in low metallicity environments to allow biospheres to develop sufficient complexity. It is only as the universe has aged, as the star formation rate has declined, as large galaxies have accumulated metallicity and settled into quiescence, that the galactic environments have become calm enough for complex life to persist over the billions of years needed. This means that the universe we live in today is, in a real physical sense, more biologically hospitable than any previous epoch. Not because of anything intrinsic to the current moment, but because the universe had to grow old enough, had to let its most violent first generation of stars burn out, had to allow the stardust from those first generations to be recycled into quieter, longer-loved stars in chemically enriched galaxies before complex life could persist anywhere. We exist in the calmer universe. Not the universe as it was at its most energetic, but the universe as it has come to be after 13.8 billion years of evolution. That is not a small thing. The conditions that allow a planet to host a complex biosphere for long enough to produce organisms capable of doing science are not universal constants of the cosmos. They are hard-won achievements of cosmic evolution, the result of billions of years of star formation and stellar death, heavy element enrichment, and galactic settling, the gradual decline of the most violent processes in a universe that began violently and is slowly learning, if that word means anything here, to be less so. We exist in that window of quiet. We have telescopes, we have equations, we have the data from 10,000 gamma-ray bursts, and we have the physics to understand what they are. The next decade of gamma-ray burst science will bring significant new observational capabilities. The Rubin Observatory, the Large Synoptic Survey Telescope in Chile, will conduct a continuous survey of the optical sky with unprecedented depth and cadence beginning in 2025, enabling real-time detection of GRB afterglows in the optical even without a trigger from a gamma-ray space telescope. The Einstein probe, a Chinese-led X-ray telescope launched in January 2024 with a wide-field lobster eye optic providing all-sky X-ray monitoring at 100 times the sensitivity of previous wide-field X-ray surveys, will detect the X-ray afterglows of GRBs with much greater completeness than any previous instrument, particularly for soft X-ray transients, like the off-axis afterglows of short GRBs that current instruments miss. The planned upgrade of the LIGO Virgo Cagra gravitational wave network to A+ sensitivity, and eventually the Einstein telescope, will extend the gravitational wave detection horizon for neutron star mergers from a few hundred megaparsecs to billions of light years, converting short GRB gravitational wave coincidences from rare events to a routine observational program. Each of these developments will bring new data on the rate, energy distribution, and physical properties of GRBs, data that will progressively sharpen the threat calculations and refine the Fermi paradox implications. The most important near-term development for the threat assessment is probably not from space, however. It is the continued expansion of the 21-centimeter radio survey programs searching for the signatures of cosmic reionization, the epoch when population 3 and early population 2 stars and GRBs together transformed the neutral universe into the ionized one we inhabit. Understanding when and how reionization occurred constrains the early universe GRB rate directly, because the two processes, reionization and GRB production, share the same progenitor populations. A precise measurement of the reionization history constrains the GRB history. And what they are, in the end, is the universe being honest about itself. It is beautiful. It is terrible. And it is, in ways that we are only beginning to quantify, the very thing that made us possible. Because the explosions that could kill us are also the explosions that forged every atom in our bodies and scattered them across the galaxy until they found their way here. The most terrifying thing in the universe made you. It is worth knowing that.